Welcome to the Vodcast and integration using Trig substitutions. What you're looking at are a bunch of different integrals, and the ones that are in the center are the ones that we don't know how to integrate yet. If you let u be equal to 4 plus x squared, over here when there is no du, same thing for this one, same thing for this one, there's an x squared on top, and basically the same thing for this one. What I have on the left is just that before you start using this method, which I'm going to explain to you, make sure that there's nothing else that works. What's on the left, if you have, or let u be equal to 4 plus x squared, u is just going to involve an x, and so this integral is involve a natural log. Over here on the right, if you let u be equal to 1 minus x squared, there's that x again, that du, and so this is going to be basically the integral of u to the 1/2. Over here on the right, well, I can actually factor that bottom, 9 minus x squared, into 3 minus x and 3 plus x. And so I would use partial fractions in order to do this one. But the ones that are in the middle are something that I don't know how to integrate yet. And that's what we're going to be doing using the idea of trig substitutions. Now, before we do that, I want to get into some identities just to make sure you know them. Certainly, there's the basic identity, cosine squared plus sine squared is equal to 1. If you were to subtract sine squared from both sides, you're going to get 1 minus the sine squared is equal to cosine theta. If you were to divide each of these by sine squared, excuse me, not sine squared, but cosine squared. If you were going to divide each of them by cosine squared, you're going to get 1. Sine squared over cosine squared is going to be tangent squared, and 1 over the cosine squared is going to be the secant squared. So we're also going to be using that identity as well. Now what's down below is something that's optional. We're going to be needing to integrate the cosine squared and the sine squared. One way of integrating these is using integration by parts. Another way of doing these is just using this trig identity, which comes from the double angle formula for this one and for this one. We'll get back to those when we need to. Now, before we even get into it, when I talk about a trig substitution, what I'm not talking about is an integral that looks like this, because what I can do with this, if I let u be just equal to the sine of x, then I can see that du is going to involve the cosine of x dx. So that's just going to become the integral of u to the third. That I can do. Don't forget that the derivative of the tangent is the secant squared. We also know that the derivative of the arctangent is 1 over 1 plus x squared, which also tells me that the antiderivative of 1 over 1 plus x squared is going to go right back to the arctangent of x. So what I want to do is look at a problem that's actually similar to this one, except instead of having a 1 plus x squared, we're going to have a 4 plus x squared. So what I have over here in the top right is this identity, 1 plus tan squared is equal to the secant squared, and I've taken the denominator 4 plus x squared, and what I'm going to do is I'm going to let x squared be equal to the 4 tan squared theta. The reason for that is if I substitute in for x squared, I'm going to have 4 plus 4 tan squared theta. Factor out the 4, and I get 1 plus tan squared theta, and I know from my trig identity that 1 plus a tan squared is equal to the secant squared, and that's the idea of these trig identities, is you do it, and I do a substitution, and I end up with something squared. In this case, the secant squared. Now, instead of starting with x squared, what I usually start with is x, in the sense that I'm going to let x be equal to the square root if I have something added to each other, like 4 plus x squared. I'm going to let x be equal to the square root of this 4, 2, and I'm going to let that be x then be equal to 2 tangent theta, so that x squared is equal to 4 tangent squared theta. Don't forget, whenever you do these problems, I also have to substitute in for dx. Well, if x is equal to 2 tangent theta, then the derivative is just 2 secant squared theta d theta. So let's substitute in. So what I have is 1 over that 4 plus x squared becomes 4 secant squared theta. The dx is going to become 2 secant squared theta d theta. Let's simplify that. Let's bring out the 2. Let's bring out the 1/4. Well, I have, that's over 1, so the secant squares are actually going to cancel. So when I bring everything out, I'm actually going to be left with just 1 times d theta. Again, this is the reason this dx or this d theta is always so important. It has to be there. But in this case, when I integrate 1 d theta, I just get theta plus c, or 1/2 theta plus c in this case. Don't forget that whenever you do a substitution, you have to put it back in terms of the original variable. Well, if x is equal to 2 tangent theta, divide both sides by 2, so tangent theta is equal to x over 2. And solve for theta, that means that theta is just going to be equal to the arctangent of x over 2. So we're going to put that back in, and our final answer is going to be 1/2 arctangent of x over 2 plus c. And notice, similar to what we had before, in this case we have a 1/2, we have an x over 2. So the idea is this, is if you come up to an antiderivative, if you come up to an integral that you can't integrate, that it's going to involve something plus an x squared. And I'm going to write that something as a squared. In this case, I always have a perfect square. I have 25 plus x squared plus 16. It doesn't have to be a perfect square, but I'm going to stick to that for the moment. What we're going to do is use the substitution x is equal to a, or the square root of that, times the tangent of theta. And again, I want to emphasize, always make sure that you can integrate it in another way before you approach using this method. So let's do this. Let's try this one. The integral of x squared dx over 25 plus x squared. Can you actually do a substitution and show that it's equal to 5 times the tangent squared theta d theta? Okay, if you let x be equal to 5 tangent theta, then dx is 5 secant squared theta d theta. Don't forget, if we use that substitution, then theta is equal to the arctangent of x over 5, and we also certainly need x squared is equal to 25 tan squared theta. I've written this out for you so you can see it. If I do all of those substitutions, what my original integral is going to look like is this. I've substituted in for x squared, substituted in for the x squared over here, substituted in for dx. Well, I'm going to factor out this 25, and then this 25 over here is going to cancel, and then I have, really all I have left is this 5. So when I do that, it's going to look something kind of like this. That 1 plus the tan squared down below is going to be a secant squared. And when that secant squared down below cancels with the secant squared up top, I have 5 times the tangent squared of theta d theta. Now this is something we actually haven't integrated yet. The way to do this is that there is a trig identity for this one as well. And so if I know from my original identity of 1 plus a tan squared is equal to the secant squared, if you solve for the tangent squared, that's equal to the secant squared minus 1. So instead of writing the tangent squared, what I'm going to do is put in the identity secant squared minus 1, and that I can integrate. Because what's the antiderivative of the secant squared? Tangent. What's the antiderivative of 1 d theta? That's just theta. There's my answer, but again, always remember to put it back in terms of the original variable once you've actually found the antiderivative. Well, I know that tangent theta is just 5 tangent theta is x, so tangent theta is just going to be x over 5. And theta in this case is going to be the arctangent of x over 5. So let's plug those back in, and we get to our answer. Simplify it out, x minus 5 arctan of x over 5 plus c. Not an easy problem, but definitely very doable. Let's try another one. And all it's seemingly looks like a simple problem. It actually involves a lot of different things and it's fairly complex. What we're going to do when I have a number minus x squared is I'm then going to use the identity 1 minus the sine squared is equal to the cosine squared. And what I'm going to do is let x be equal to the sine of theta. And the reason for that is if I have 1 minus x squared and I let x be equal to sine theta, then x squared is the sine squared theta, and 1 minus the sine squared is equal to the cosine squared theta. And what I have behind this box is just remember that if x is equal to the sine of theta, then theta is equal to the arc sine of x. And also I'm going to add the fact, remember from pre-calculus, if you have the function arc sine of x, that the principal values for theta go from negative pi over 2 to pi over 2. Let's substitute everything in. So 1 minus x squared becomes cosine squared. So this is the square root of the cosine squared theta. Dx, can do dx. Well, what is dx? Dx is equal to the cosine theta times d theta. Substitute that in, so this is times cosine theta d theta. Whenever I have the square root of something squared, it's always going to be absolute value, at least to start with. And this is the reason for looking at the principal values. If theta is limited to negative pi over 2 and pi over 2, then the cosine theta is always going to be greater than 0. In other words, we're between quadrants 1 and 4, so cosine is always going to be positive. And if cosine is always positive, therefore I can drop this absolute value, and I'm going to have cosine times cosine, and so I'm going to get cosine squared theta d theta. Well, how do I integrate that? Well, remember I mentioned in the beginning is you can use integration by parts, or actually what I'm going to do is actually use that trig identity. This trig identity is the cosine squared theta is equal to 1 plus cosine. Again, note that the argument doubles. 2 theta over 2. So I'm going to rewrite cosine squared as 1 plus cosine 2 theta over 2 d theta. Well, let's rewrite that. Let's write that as 1/2 plus cosine of 2 theta over 2 all times d theta. Let's integrate that with respect to theta. And so I'm going to have 1/2 theta plus the integral of the cosine is the sine. So the integral of the sine of 2 theta is, the integral of the cosine of 2 theta is sine of 2 theta. Divided by 2, it's already over 2, so that's over 4. Well, now the challenge here is going to be to get this all back in terms of x. My theta should have a line through it. I can't quite get that. Well, I know that if x is equal to the sine of theta, then theta is equal to the arc sine of x. That's easy. But I have the sine of 2 theta, and I just have sine theta here. How do I put that back in terms of x? Well, I'm going to introduce another trig identity. This is from the double angle formula, that the sine of 2 theta is equal to 2 sine theta cosine theta. So this is equal to 1/2. Let's just keep it as theta for right now. Sine of 2 theta is 2 sine theta cosine theta all over 4 plus c. So now we can substitute in. Well, theta is equal to the arc sine of x. 2 over 4 is just 1/2. Sine theta, well, what is sine? Well, sine theta is just x. Well, what's cosine theta? Well, I'm going to go back to these triangles that we've set up when we used this substitution. The sine of theta is x over 1, which means if this angle is theta, then the opposite is x and the hypotenuse is 1, which means, using Pythagorean theorem, this adjacent side is the square root of 1 minus x squared, Well, given that setup, what is the cosine theta? Well, that's going to be the adjacent over the hypotenuse, and so that's just the square root of 1 minus x squared. So we're going to substitute that in for cosine. And so that's going to be the square root of 1 minus cosine, 1 minus x squared, and then all of that plus c. As I said, it's a pretty complicated problem. Okay, let's try one more. And before I do that, what I want to mention is that whenever you see a squared minus x squared, again, make sure you can integrate it before. 9 minus x squared, 25 minus x squared. What we're going to be doing is using the identity x is equal to a sine theta. So can you try this one? Can you take this problem and can you use a substitution and can you turn it into 9, this integral of sine squared theta? Give it a try. Okay, here it is. I really hope that you tried that one because these are pretty difficult. If I let x be equal to 3 sine theta, and the 3 comes because it's the square root of 9, and it's the sine because it's 9 minus x squared. Everything kind of follows from that. If x is equal to 3 sine theta, divide by 3, theta is equal to the arc sine of x over 3. Take the derivative of sine is the cosine. Don't forget that d theta. And if you square that, you're going to get 9 sine squared. So I've actually written this out so you can see this. So I'm going to put all those substitutions in. And it's going to look something kind of like that. X squared is 9 sine squared theta. X squared is 9 sine squared theta. Dx is 3 cosine theta d theta. What I've done over here on the right is based upon this substitution, the sine theta is equal to x over 3 in this case. So theta is the angle, this is x, and the hypotenuse is 3. Given that, let's just go right to it, that third side is then going to be equal to the square root of 9 minus x squared, and the cosine theta is going to be equal to that. We'll be needing that in just a minute. Because what we get down to when you simplify this, the 9 minus 9 squared, you factor out the 9, but that actually the square root of 9 becomes 3. And 3 times 3 is 3 on the bottom and 3 on the top. So those 3's cancel, leaving me with just 9 in front. The square root of 1 minus the sine squared becomes the cosine squared. The square root of the cosine squared is going to be the absolute value. But again, given the principal values of that function, the cosine theta is going to be positive. So that's a lot going on in that one. But this turns out to be that when this square root of cosine squared is cosine, the cosines are going to cancel, and I'm left with just that. A lot of work to get to that point. You might want to go over it again. We now have to integrate that, and that's where I'm going to use that trig identity. Sine squared is equal to 1 minus, in this case, cosine 2 theta. So it's almost exactly the same. So I plug that in. I'm going to integrate that. I'm going to use that trig identity of sine of 2 theta is equal to 2 sine theta cosine theta. Then I can substitute in theta is equal to the arc sine. Sine theta is equal to x over 3. Cosine theta is equal to the square root of 9 minus x squared. And finally, at the end, we're going to get that. Challenging problem. Take care.